So this is how we do to obtain the adjustment equations for the combined adjustment. We have to set up the non-linear model, which is here, a function of x and L parameters and observations. And then we derive, we linearized this general nonlinear model using Taylor series. And so this is the function to be linearized. The symbol here, it indicates that there is an approximation because higher order terms of the Taylor series expansion are disregarded. And then we have evaluation of the original model by means of the approximate values of the parameters and of the observations, even though here we know that when we do the evaluation we use the actual observations, but I'm using the same symbology here. Then we compute the partial derivatives of the model with respect to parameters, evaluating the model with the approximate values. This is the mismatch between the parameter and its approximate value. Then we have the partial derivative of the model with respect to the observations L, again evaluating it at the point of expansions or the approximate values of observation parameters. And here we have the mismatch between observation and the approximate value of observations. So these terms, we can replace them. This is W, this is A, this is delta, this is B, and this is R. Okay, and now we use the exact, we make it exact equal to 0. Of course, if we're linearizing a non-linear model, therefore it will imply that we need iteration. If the model is already linear, we don't need iteration. What is done then is we impose a condition. This is the least squares condition. The minimization of the weighted squares of the residuals. So this is accomplished by, this is a scalar, by the way, that's phi. It is accomplished by multiplying the transpose of the residual vector by itself, and we use the covariance, the inverse of the covariance matrix of the observations as a weight matrix. This least squares condition will then be applied, will be imposed onto the linear model. So this is the model that we have obtained from Taylor series expansion. So this is the least squares condition, and this term here, 2 times k, is just a scalar. K is known as the Lagrange correlates. It is put in here in such a way that the result of this term between parentheses, it is conformed. Well, it becomes a scalar essentially, and then we can add that. So they're equal to 0. Okay. We then evaluate these function, this equation. We call the variational function. And we evaluate that with respect to parameters here, to residuals, and to the Lagrange correlates. And this is what we obtain, the evaluation for each one of them. So here we have the three equations that are the final equations. And now we are using these symbols hat because we have imposed the least squares condition. Delta will be used as a correction to the approximate value x naught to obtain the final parameter x hat. And the residuals here, the residual vector, will be added to the observations represented here by L naught in such a way that we obtain the adjusted observations. Now, this is not the solution. This is just a system of normal equations. How are we going to obtain solutions for delta and for R? We're going to obtain a solution for delta and for R by organizing those three normal equations in a system of a hypersystem, if you want to call that. And the arrangement is made in such a way that we can apply the rules of parameter elimination by partitioning. So this is vector n11, this is vector n12. Here we have vector n21, here we have n22, here we have y1, here we have y2, here we have u1, here we have u2. So we're going to apply the rules of parameter elimination by partitioning. We have three unknowns, r, k, and delta. We eliminate r, then we eliminate k, and we find a solution for delta. Then we can back substitute to get back substitute to get a solution for k and then a solution for r. So this is here listed the solution for delta and for r, the least squares solution vector, least squares correction vector, and the least squares residual vector.